Good afternoon, class. My name is Justin, and today we'll be working on Chapter 3 of AP Chemistry, Stoichiometry of the Zundal textbook. Last week, we started learning about naming binary compounds. Typically, what are the names for ionic compounds? What are the names for ionic compounds that list transition metals? Ionic compounds that include polyatomic anions and/or cations, as well as covalent atoms. Zooming into this page here in the contents, we see these sections. 3.1 is counting by weighing. 3.2 atomic mass. 3.3 is the mole. 3.4 is molar mass. 3.5 is percent composition of compounds. 3.6 is determining the formula of a compound. 3.7 is chemical equations with subsections chemical reactions and the meaning of a chemical equation. 3.8 is balancing chemical equations. 3.9 is stoichiometric calculations. And 3.10 is calculating involving limiting reactants. So we'll start off with 3.1, which involves how to measure masses of chemicals. On the next page, we have an introductory paragraph in which we learn this new word, stoichiometry. Stoichiometry comes from the Greek word stoichon, which means element, and metron, which means to measure. There are roughly 118 elements that exist in the periodic table, and each of these elements contain an atomic weight. The atom itself is composed of the nucleus, which contains most of the mass, and this nucleus consists of protons and neutrons. These protons and neutrons weigh roughly the same 1 AMU, which stands for atomic mass unit. Before equipment was able to really find the masses of the proton or the neutron, 1 AMU was defined as 1/12 the mass of a carbon atom. When looking at the periodic table of a carbon atom, we see that the average atomic mass is given as 12.011, which rounded to the nearest whole number is actually 12. This is due to the fact that the most abundant isotope of carbon contains 6 protons and 6 neutrons. Well, what is an isotope? From our previous week, we know that isotope means an atom with a different number of neutrons. For the case of carbon, 2 isotopes exist. There's carbon-12 and there's carbon-14. We know that the identity of carbon is solely based on the number of protons, 6. So therefore, when you add the number of protons and neutrons, it tells you indirectly how many neutrons will exist for each of these cases. For example, for carbon-12, there will be 6 neutrons, because 6 of them must be protons. And for carbon-14, there will be 8 neutrons. To give another example of isotopes, let's look at the case of hydrogen, one of the most abundant atoms in our entire universe. In fact, the sun burns hydrogen and turns it into helium in order to give life on Earth. When we look at the average atomic mass of hydrogen, the number is given as 1.008. What are the isotopes of hydrogen? Well, the most abundant ones are hydrogen 1, where the bottom number tells you the number of protons and the top left number tells you the number of protons and neutrons. And in this case, we see that there's exactly 1 proton and we have 0 neutron. Another isotope would be hydrogen 2, in which case the upper number is no longer 1 but instead 2, where there's 1 proton and there's going to be 1 neutron. And this is also referred to as deuterium. Finally, hydrogen 3 consists of 1 proton and 2 neutrons, and this is referred to as tritium. So what's very important about these different isotopes of hydrogen is the relative abundance that exists in nature. For example, hydrogen 1 exists 99% of all the different types of isotopes of hydrogen. Hydrogen 2 would only consist of 0.01%. And lastly, the hydrogen 3 would be a very small trace amount, a value that's so much smaller than 0.01%. And in doing so, what we use to calculate the average atomic mass would be the relative abundance times the atomic masses of each of those isotopes. So we would get 0.9999 times 1 for the abundance 99.99% as well as the 1 atomic mass. We add this with then the 0.0001, the relative abundance of hydrogen 2 or deuterium with its atomic mass, which is going to be 2. And of course, we will have 0.00000, I would say 1, a very trace amount with the atomic mass of tritium, hydrogen 3. And when we use this, we actually calculate this exact value of the average atomic mass. So the most important thing about these average atomic masses is the fact that this will tell you the relative abundance in nature of the atomic weights. Earlier, I introduced you to the concept of AMU, atomic mass unit, which is the mass of 1/12 of a carbon atom. So the question is, why is AMU important? Well, we refer back to Avogadro, who was a very famous scientist who did not quite find this exact number, but predicted the fact that there must be a number of atoms such that the AMU representation of that atom, aka the number of protons and neutrons, typically the average atomic mass. Once you have a definite quantity of hydrogen atoms, the total mass of that quantity of atoms should be equal to 1 gram. And that was what is referred to as Avogadro's number. If we have exactly an Avogadro's number amount, and each of those hydrogens has an average mass of 1.008 AMU, then that'll yield exactly 1.008 grams of hydrogen. And in fact, this number has been later found, not attributed to the scientist who actually found it, but to Avogadro, who first conceptualized it. And this number is equal to 6.022 times 10 to the 23rd atoms, or molecules, per mole. And so this is by definition a mole, spelled MOL. And when we further this theory, let's look at an example of aluminum. Aluminum is a metal that is used in the aerospace industry, and the atomic mass, or the average atomic mass, is 26.982 AMU. Now, if we were to have 1 mole of aluminum, this would consist of 26.982 grams. Another example would be gold. Gold has a symbol AU, and its molar mass is going to be 196.97 AMU, such that 1 mole of gold will be equal to 196.97 grams. And so this value AMU, you can think of it as a conversion factor between grams and moles, such that the molar mass now becomes synonymous with this AMU. If we look at another example like sodium, Na has 22.990 AMU. And so therefore the conversion between grams, the mass that we use in the SI system, and the number of atoms, which we specify with moles, is going to be 22.990 grams per mole. And you might see it simplified, written as 22.990 G divided by MOL. Now I'll provide you with a symbol that allows you to calculate anything between moles, grams, and a number of atoms. So in the middle of this chart, I'm going to have the symbol for mole, which is typically written as an N. On the right side is going to be the number of atoms, or we could specify molecules. And on the left side, we're going to have the mass, which is written in grams. And so the idea is every time you wish to go to moles, because moles N in itself is going to be the intermediary, you're always going to be dividing by a certain quantity. From grams, in order to reach moles, you must divide by the molar mass. And in order to go from the number of atoms to the number of moles, you have to divide by Avogadro's number. And I'll write this as 6.022 times 10 to the 23rd. Now the reverse direction, starting from moles, to go to the left in mass, you must multiply by the molar mass. And likewise, in order to start from moles and go to the number of atoms, we must multiply by Avogadro's number, which is going to be 6.022 times 10 to the 23rd. And so what sort of problems you would expect is you're going to be given either a quantity of mass, like let's say you're given 3 grams of hydrogen. You must then find the number of atoms of hydrogen. So if we were to start at mass of hydrogen, we must divide by the molar mass, which in this case is going to be 1.008 based on the periodic table. So then we've gone into this intermediary junction, to which then we continue on to the number of atoms by then multiplying by Avogadro's number. So quick rule of thumb is multiply when you are going away from moles and divide when you are going towards moles. So looking back in the book, Section 3.2 specifies just how the atomic masses and the isotope masses were calculated based on using something called the mass spectrometer that you can do reading on your own. It involves magnetic fields and magnetic forces, something you won't really dive into until you take a physics class. In this section here, we see a relative example of how to calculate the average atomic mass using the abundance percentages times the AMU relative and adding them together. The mole here is what we discussed earlier with the fact that the quantity of the mole is equal to 6.022 times 10 to the 23rd. And here the book says very difficult to imagine. And now we could do sample exercise 3.5 just to reinforce the idea of how to use this chart. So zooming in on the book, we have 3.5 given. Cobalt is a metal that is added to steel to improve its resistance of corrosion. Calculate both the number of moles in the sample of cobalt containing 5.00 times 10 to the 20th atoms and mass of the sample. So we are given number of atoms is 5.00 times 10 to the 20th atoms. Our chart from before, we have N, which represents moles in the middle, and we have number of atoms, and we have mass. Now recall that anything that essentially goes towards the number of moles, we must divide by a certain quantity. So for mass, we have to divide by the molar mass, which I'll indicate with little m, capital M. Those are the atomic masses that are provided in the periodic table. In order to go from number of atoms to number of moles, we have to divide by Avogadro's number, 6.022 times 10 to the 23rd. And likewise, the opposite direction will be the inverse operation. For division, the inverse is multiplying, 6.022 times 10 to the 23rd. And for molar mass, must be multiplied from grams. And so as we look at the periodic table, we have to find where is the cobalt is located, which will be atomic number 27, where the molar mass is going to be given as 58.933 grams per mole. And so therefore, in order to find the number of moles, moles will be equal to the number of atoms, 5 times 10 to the 20th atoms, all divided by Avogadro's number, 6.022 times 10 to the 23rd. Make sure you input this information correctly into your calculator. And according to the answer of which is going to be 8.30 times 10 to the negative 4 moles of cobalt, as given in the problem. And now that we have this many moles, in order to find the mass, we must then multiply by the molar mass, which I'll get my periodic table again. Cobalt is given as 58.933 AMU. So we do 8.30 times 10 to the negative 4 moles of cobalt. We multiply this by 58.933 grams per mole. And so the unit of moles will cancel out, which gives us a product of 4.89 times 10 to the negative 2 grams. Zooming out onto the next page, we discuss molar mass. The idea of molar mass is that this concept of atomic mass can now be applied to molecules themselves. For example, what we see here is we have this molecule CH4, which is an organic molecule which would have been named carbon tetrahydride due to our non-metal covalent naming scheme, but in this case this actually has a special name, like all organic molecules do, known as methane. We know that the molar mass of carbon is going to be 12.01 grams per the periodic table, as we've seen, and likewise the hydrogen is going to be atomic mass of 1.008, but this molecule consists of 1 carbon and 4 hydrogens, so that the molar mass of the entire molecule is going to be the sum of all its constituent parts. Therefore, it's going to be 16.04 grams per 1 mole. Building upon this concept, you will have problems in the future that consist of more complex molecule, like this one for sample exercise 3.6, juglone, which has a chemical formula of C10H6O3. We know that the atomic mass of carbon is going to be 12.01. We also have hydrogen. Now we're introduced to another very popular atom, which is oxygen. Oxygen is going to be the gas that we breathe. This juglone, the molecular mass can be found by multiplying the individual atomic masses by the quantity based on the subscript, so that 10 carbons will be 120.1 grams. Hydrogen, 6 of them will be 6.048 grams. Oxygen, 3 of them will be 48 grams, and so the mass of 1 mole of this compound is going to be 174.1 grams per 1 mole. Now with these fundamentals alone, you pretty much have all the tools necessary in order to find the molar mass of any compound. That is just going to be, in this process, whatever is going to be this symbol or this symbol that allows you to translate from mass to moles or moles to mass, vice versa. If we look closely at sample exercise 3.7, calculating molar mass 2, closely related to juglone that we did earlier, we want calcite, calcium carbonate. So the atomic mass of calcium is going to be 40.08 grams per mole, as given in the periodic table. This will be element number 20. As I bring the periodic table here, calcium is located right here, 40.078. Carbonate is going to be one of those polyatomic anions that consists of carbon and oxygen. Earlier, we found carbon is going to be 12.01 and oxygen is going to be 16.00, and they calculate the molar mass of calcium carbonate as roughly 100.09 grams per mole. Now, part B says a certain sample of calcium carbonate contains 4.86 moles. Moles are given here. What is the mass of the sample? In which case, we wish to find this mass, which is going to be multiplied by the molar mass of 100.09 grams. Now, they may also ask for you to find exactly the moles of carbonate, and so now what we need to do is we need to find the molar mass of just the carbonate itself, which is going to be 60.01 grams, due to the fact that there's 12.01 grams of carbon and 48 grams of oxygen with each oxygen having 16 grams with a quantity of 3 oxygen, and they multiply because moles, whenever you move away from moles, you have to multiply by a certain quantity, and you get the answer here. With this much theory understanding, now I would like for you guys to go to the chapter questions located on page 118, section moles and molar mass, and please do number 38 to number 55 odd. Number 33 to 58 odd. You can get the periodic table from this website, ptable.com. In order to practice using the periodic table, looking up the molar masses, identifying what the molecules' names are, and the respective quantities of the underlying atoms.